This is our first of two lectures on monotone operators and operator splitting, and it's going to take us to the derivation of Douglas Ratchford in the sequence of these two lectures. And in addition, we'll get to define a little bit more precisely things that we've seen in the past, in particular monotone operators, and we'll get to make again the connection to a more general theory of relations. So let's first start talking about an operator again. We've seen this many times. So our an operator is a mapping from Rn to Rn. It actually doesn't have to. It can change dimensions as well. But for us, we're going to be thinking about an operator from Rn to Rn, and it could be multiple valued. And as always, the primary motivation and example that we should keep in our mind, though this theory extends far beyond that, is the gradient or subdifferential. If a function is differentiable, then its gradient is a single-valued operator from Rn to Rn. If it's not differentiable, then we have its subdifferential, and at points of non-differentiability, the subdifferential is a set, so it is a multiple-valued mapping. Now, this is what we should be thinking of. Main example is the gradient of a function or the subdifferential of a function. And it's useful to think about the subdifferential or the gradient, in general an operator, through its graph, which is exactly the same way that we think about a function through its epigraph. So the graph of an operator T is going to be a subset of Rn cross Rn, and I could just draw this using each axis to represent n dimensions. This would be x, and this would be t of x. So there's no notion of ordering. I'm not talking about the epigraph as in everything above a function. When we were talking about the epigraph, we were looking at x and f of x, and the epigraph was all points xs, where s is bigger than f of x. But in this case, I'm just going to look at the points of x, comma, t of x. And so the graph of t is the set of x, t of x, or if I want to be a little more parsimonious in notation, x comma tx, such that x is in Rn. And in terms of some jargon, this graph, sometimes you'll see it called the graph of an operator. You may also see it more generally referred to as a relation. So the graph is also called a relation. And maybe we'll use R, for example, to denote this relation. So a relation is a subset of Rn cross Rn. And this is going to allow us to define a number of different operations on relations, which is really going to give us properties of operators. So this will allow us to define a little bit more carefully things like inverse. When we have multiple valued mappings, it's not natural to define, or we need a little bit of work to take care to define an inverse appropriately. So again, our main example is going to be our main example for us is going to be R is X. and subdifferential f of x, this collection. Once we've defined a relation, we can also think about generalized equations. So if we have something that's single valued, then we can, if we have a single valued operator, we can think about solving t of x equals 0 for t single valued. But for t multiple valued, we need to solve a generalized equation, which is we want to find an x, not where t of x is equal to 0, but where 0 belongs to the set t of x. Which again you'll recognize as exactly the characterization of optimality of a convex optimization, of an unconstrained convex optimization problem. So we'll also see this written in terms of relations. But it basically, we're not really introducing anything more fancy at this point. I just want to also expose you to the to jargon you might see that is discussing things that we're exploring and learning about. So you may see things like this, but they mean essentially the same thing. So you'll notice there's a little bit of abusive notation here, where I'm using R to mean to stand for the operator as well as the relation. So when you see the term generalized equation, what we really mean is really nothing more than what we've been doing when trying to use the characterizations of optimality. Defining a relation allows us to make precise a few common types of operations that we might want to use. So very important for us has been the inverse. So if R, we said a relation is a subset of Rn cross Rn, then R inverse is also a subset of Rn, and it's just defined as all pairs y comma x such that x comma y belongs to R. We can also define composition in a very similar way. So if I have relations R and S, then the composition of R and S is really writing in a relation language the natural idea of composition of an operator. So this would be all pairs xy such that there exists a z with xz in S and zy in R. And we can do a number of other things. So we can talk about scalar multiplication. For a scalar alpha, alpha R is equal to x alpha y such that x y is in R. So again, a guiding principle here should again be the gradient or subdifferential. And that will tell us immediately why it is that scaling R isn't like scaling a set. If I just have a subset and I talk about scaling, I would be scaling each coordinate. Whereas for relations, we want to really think about this as being an operator, as a graph of an operator. And so scaling really corresponds to just scaling that second, the second coefficient. And similarly, addition is not going to be the same addition of two subsets of space, but we'll really just focus on that second, the second coordinate. So it's x and y plus z, such that x, y, and xz are elements of R. And again, you would rederive this immediately if you just think about the example of the gradient or the subdifferential. One important property, or one important operation on a relation, which we have already talked about, is called the resolvent. The resolvent of a relation R is the inverse of I plus lambda R. So now we should feel comfortable with exactly what this means. Even though we had written it before for the multivalued operator of the subdifferential, now we've defined all aspects. We've defined the inverse, we've defined scalar multiplication, we've defined addition. And let's even put it all together. So what this means is this is the subset of Rn cross Rn, where of all things of the form x plus lambda y comma x, such that xy belongs to R. Again, a relation. Next, we need to define monotone. Again, something that by now we're very familiar with in the context of gradients and subdifferentials. And then a technical point, which is a maximally monotone relation, or a maximally monotone operator. A relation R is called monotone if u minus v x minus y is greater than or equal to 0 when for all pairs xu and yv in R. And again, we can think about subdifferential and the gradient, and they satisfy this. And a relation is called maximally monotone, and this is again where it helps to think about a relation as being a subset of Rn cross Rn if inclusion-wise it is the largest, it's not contained by some other monotone operator. R a monotone relation R is called maximally monotone if it is not contained. Again, just remember that R is a subset. If it is not contained in any, and I mean properly contained, in any monotone relation R prime. We're not going to be dealing too much with these with any generality beyond subdifferentials and gradients, but still, I want to expose you to this language and the jargon. There are, I would say, not generalizations, but different examples where the operators are just linear algebra mappings. A matrix will give us a linear mapping that we can think of. So there are a set of other examples that we could develop, but for us, we're going to be entirely focusing on what we get when our operators come from differentials and gradients. So for us, what we've seen that this operator is monotone if and only if. Remember, we proved both conditions in an early lecture. If and only if f is convex. And what I'll leave for you to check, again, this is a little more technical aspect of it, is that it's maximally monotone if f is also closed. So now we know what a relation is. We know the operations that we can exercise on a relation. In particular, the resolvent is going to be very important for us in the sequel, and also what it means for a relation to be monotone or an operator to be monotone and maximally monotone. We've talked about the resolvent. Let me write that down again, and then write down an operator that's related to the resolvent called the Cayley operator. Again, if I've been using R for a general relation. Let me switch to another letter so that I can use R for resolvent and C for Cayley, just to make it a little easier for us to remember. So let's let F be a monotone relation, and lambda be some non-negative value. Then the resolvent is what we just wrote down, and it's equal to I plus lambda f inverse. And if f is monotone and lambda is greater than or equal to 0, then R is non-expansive. The Cayley operator is equal to twice R minus the identity. So in other words, it's twice times I plus lambda f inverse minus the identity. And again, if lambda is non-negative and f is monotone, then C is non-expansive. And we're going to actually show this second property. And once we have the second property, we know something else about the resolvent. So note that just from the definition of the Cayley operator, we have that R is equal to 1/2 times the identity plus 1/2 C. So what does that mean? If C is non-expansive, that means that R itself is an averaged operator, because it's the average of something that's non-expansive with the identity. And in particular, because it's averaged with alpha equals 1/2, there's a special term for this. It's called firmly non-expansive. R is averaged, and in particular 1/2 averaged, which is called firmly non-expansive. A simple check is that the fixed points of R are also the fixed points of C. You can see that directly from the definition. It's also easy to see in this setting. If you average any operator with the identity, the fixed point, and it's a non-trivial average, the fixed points have to be the same. So we'll see that this is useful. In particular, we've already seen that if f corresponds to the subdifferential of a convex function, then the resolvent operator exactly corresponds to the proximal point algorithm. We've seen that the proximal point algorithm, its fixed points, are the optimal solutions to the convex optimization problem. And so right away this tells us that the Cayley operator is another operator whose fixed points are if f is given by the subdifferential of a function f, of convex function f, the Cayley operator's fixed points are going to be the optimal solutions to the problem of minimizing f of x. Okay, so let's look at the problem of showing that, so this is slide 1 out of 2 on this. Let's show that C is non-expansive. And in particular, that'll immediately show us that, that R is firmly non-expansive. So the claim is that if F is monotone, lambda is non-negative, then C is non-expansive. So we're going to break this down into 2 parts. First, we're going to show that in this setting, so first we show that if under the conditions, namely f monotone lambda greater than or equal to 0, this implies that the resolvent operator, regardless of the status of f could be multiple valued. In fact, R will be single valued. As an operator. Let's, in the midst of abstraction, it's also useful to just tie it back to realize that what we're going to show now, it's going to use the more general language that we're developing, nothing particularly fancy, but in fact we've already seen this. So if we already recall that the resolvent operator is proximal point, and you think about what the proximal point algorithm is doing, what is that prox mapping? Why is prox mapping uniquely defined? It's because it's the minimization of a convex function plus the 2 norms squared, which is strongly convex. So it's the argmin of a strongly convex function, and we know that that's unique. So we know that prox mapping is singly defined. So this isn't a surprise. We're just deriving this now in the more general terms, not restricting ourselves to the setting where f is a subdifferential of a convex function. Okay, so let's show this more generally. What do we need to show? And this will be the first step to showing that the Cayley operator is non-expansive. We need to show that if xu and yv are in our resolvent, then if x is equal to y, it must be that u is equal to v. Then x equals y implies that u equals v. And of course, if x doesn't equal y, then we don't care. Okay, so if xu and yv are in R, what is that? What do we have? So let's take this one step at a time. Then we know that ux, I flip them, I'm using the inverse, ux and vy are in I plus lambda f, because xu being in R means that xu is in I plus lambda f inverse. So this is the definition of inverse. Again, just part of the benefits to having defined this in a precise way. We don't have to wonder what inverse means. This is exactly the same as, I'm just writing out what this means, that x is an element of u plus lambda f of u, and similarly y is an element of v plus lambda f of v, which is the same as writing x minus, which implies, what I'm going to do is subtract these from each other. X minus y is an element of u minus v plus lambda of f of u minus f of v. Everything here we've defined. We've defined what it means to, what a scalar multiple of a relation is. We've defined what addition and therefore subtraction of these relations are. So now note, so check, let's make sure we understand this. So this means that u minus v times x minus y is u minus v squared plus lambda times u minus v f of u minus f of v. So I didn't mean to write equality here. So what I mean to write is it's an element. So I have vectors, so x minus y is a vector, and it's an element of a subset of vectors that's on the right. And therefore, if I multiply if I take the dot product of x minus y with something, that should be an element of the dot product of u minus v with all of those vectors that were on the right before. So this is what this means. And now finally I can use the key aspect, our key assumption that f is monotone. So f monotone and lambda non-negative means that this, no matter what value I choose, is greater than or equal to 0. So, and this is the only element I have on the right that's actually a set. So in other words, what this is saying is that u minus v, x minus y, belongs to the set that looks like u minus v squared plus some non-negative scalar. But that immediately implies that u minus v, x minus y, is greater than or equal to u minus v squared. And if u minus v if this dot product were an element of a set that's something plus a bunch of things on the positive orthant, then u minus v x minus y has to be greater than or equal to. I didn't mean positive orthant. I just mean non-negative. At this point, we took the dot product, so it's non-negative. And now we're in business. This is exactly what we needed to show, because this exactly implies that if x equals y, what happens? The left-hand side is 0, therefore the right-hand side is less than or equal to 0, therefore equals 0, and this means that u equals v. So this is what we wanted to show. So far we've shown that R is single-valued. Again, something that we had reasoned using strong convexity in the special case where f is the subdifferential of any convex function, and R is its resolvent, which again is equivalent to the prox mapping. Okay, so now let's conclude that C is non-expansive using this. So what do I need to show? I need to show that C of x minus C of y is at most x minus y. This is what we want to show. And let's do the calculation. So remember again that C is equal to 2r minus I. And so C of x minus C of y is equal to 2u minus x minus 2v minus y squared, where x, u, and yv are in R. In other words, to use notation just a little bit, I'm writing that u is equal to R of x. Note that I'm using the single valued property. And v is equal to R of y. Rearranging, this is equal to 2u minus 2v minus x. Now let's make sure the minus signs are all right. I've got a minus minus y, so plus y minus minus y. That's just equality here. And expanding out, I'm using the 2 norm. This is equal to 4 times u minus v squared minus twice the cross term, u minus v x minus y, plus the last term squared. And this is less than or equal to x minus y squared. So make sure that you see how I did this this last step. This is again just using what we already saw on the previous slide. So in other words, this is non-negative, is non-positive. So if I drop it, I only make things bigger, and c of x minus c of y is exactly, I have exactly what I want. So this shows that c is non-expansive, and therefore r is firmly non-expansive. What we're going to pick up with next time is showing how C can be used as a good way to do splitting when we have the sum of f of x plus g of x. Similarly to how we've already seen using proximal gradient as a splitting technique, C, the Cayley operator, is going to give us a different splitting algorithm. So we're going to pick that up next time.